we're going to take a look at graphing some relations, and then we're going to state the domain and range, and then determine if the relation is actually a function. So here we have the square function, y is equal to x squared, and I'm just going to start off by making a table of values, all right, to figure out. Now I know that most of you know that this makes this shape, but let's just get some specific points, because if you're asked to graph, then most likely, unless it says sketch, most of the time they want you to really get some specific points. So I'm going to go ahead with a couple of negatives, 0, and a couple of positives. Now when I look at this, to drop in, to input a -2, I'm not going to have any problems with the function, with the output. In other words, I'm not going to break any math rules by putting in a -2, and so that's going to be fine to just put in -2. We get out of 4. I put in a -1. I get out of 1. This I get 0, 1, and then 4. So let's go ahead and plot the points. I'm going to start with 0, 0. So let's put in our -2, 4, and oops. Got a -1, 1, and 1, 1, and 2, 4. So this is called an even function, which just means it's symmetric about the y-axis. So, oops, that was kind of messy. Let me try that again. Okay, so there's the function. Now we can immediately look at that and say that this is the relation, and we can look at that immediately and say that indeed it is a function. So this answer is yes, it's a function because it passes the vertical line test. Now, the issue though is, how do we decide what the domain and range are? Well, I'm going to do a visual illustration really quickly about how to find domain and range, and then later on in a video or two we talk about how to determine domain and range if you can't even figure out what the picture looks like. So for domain and range, I want you to imagine that this x-axis is a very strong magnet, and that these the red lines right here that we see that create the graph are really small little particles of metal. If I turn on this really strong X magnet, which is related to the domain, I turn this on, here's what's going to happen. All these little red particles are going to go as fast as they can straight to the magnet. And if that happens, all these come straight down, and we know that the red graph continues to go out, out, out. So that means that the red particles continue to come down, 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 which means that in the end, this whole graph is going to be filled with red particles. Well, that, folks, is the domain. In other words, it's from -infinity to infinity, or you could say that it's all real numbers. You could also put it in set builder notation, x such that x is an element of real numbers. So any way you want to write that. Most college level classes are writing domain in interval notation, which is what I'm going to probably do for the rest of these. So let's go ahead and take a look at the range. For the range, I'm going to go ahead and just kind of ignore. If I try to erase that red, it'll mess up my x-axis. So I'm going to, now let's take a look at the y-axis, and let's pretend like that the y-axis is a very strong magnet. If I turn on that very strong magnet, all of these red metal particles are going to come as fast as they can to stick to this really strong magnet. And the question is, what would be covered in red at that point? Well, everything here and up would be covered in red. So, right? Convince yourself of that. From 0 up would be covered in red. Well, folks, that's my range. From 0 to infinity. All right? From 0 to infinity. You could also write it this way: y such that y is greater than or equal to 0, meaning we're including the 0, and that's set builder notation. Oops, excuse me, forgot to include that y is an element of the real number system. So here we go. Y is an element of the real number system. Okay? So there's how to find domain and range visually with a picture. All right? Thanks for watching. Hope this helped.